Okay, we are on the record now. Oh, good. Here's my little cheat sheet. And another one. Here is your entertainment for the weekend. And is it right that everyone has completed the little game with spin operators? That I can collect it now?
I think it's due on Tuesday.
Okay, so you will bring it next time.
You also mentioned it as yesterday.
Like some of you
Weekend
have
entertainment.
prepared. Well, it's better if I collect all at once.
Okay.
Please do not forget them.
Okay.
Who we are and what are we doing? Let's go over this homework. Probably it would be most interesting. I see you do have your attention attracted to this piece of paper. Right? This one. So when we met in the lab last night, we took the models that we have created 2 weeks ago and applied 2 things to it. First, we optimized it with force field, optimized geometry, and then taking the geometry upon optimization, we found the total energy in Hartree-Fock method, which we are slowly picking up through the lectures, but for practical reasons we can run it already, because it is just the symbol HF in the method, that's it. So it would be pleasant for me and beneficial for you if you make snapshots of optimal geometry for each of the model and add 2 numbers, total energy by force field and total energy by Hartree-Fock. The total count of models is very large, so it will help you to develop a practical skill of submitting multiple jobs without thinking with large numbers, because you may need it later. And the scientific idea behind it is that later we will see that for the same chemical composition, one can get substantial change of the properties by alternating the lengths of a chain or size of a piece of material. So first group of models is polyene chain with single-double carbons and hydrogens terminating it. So changing the n from 1 to 6 if you have steam, and maybe few values less if you get tired, but try several, and make sure that they are linear. If they are curved isomers, it will be also fun. A lot of interesting observations and findings, but for simplicity it's better to keep them linear. The second one is titanium dioxide terminated by hydrogens, where this titanium 2 group can be replicated n times. Right now we do have 1 and 2, but you can go up to 4. If you haven't drawn it, you can quickly click, and then draw for it. The C is the minimalistic quantum dot, which is analog of carbon hydrate adamantite, with replaced carbons to silicons. So it is silicon 10 with several hydrogens around it terminated. And the last one is model for lead halide perovskite to the best of your knowledge. Just try if the software will be able to chew this model at all. Some models are challenging for the software. They explode or bring software to the error. Let's put a star here. And if you have completely nothing to do, if this doesn't exhaust you, you may prepare one slide summary of Hartree-Fock from Wikipedia or from like some open sources, so that you read a little bit. Do not spend more than like 5-10 minutes on it. Look forward what you understand of this method ahead, and make some brief summary. What do you expect from it? Like a picture or equation or a couple of sentences. We will not present it in public. I will just look on this piece of paper and say, good. Oh, someone can sit in this and, and look to the sides. So we are building fundamentals for computing properties of molecules and materials by computational programming. We have separated electronic and nuclear degrees of freedom due to Born and Oppenheimer, and now we are focusing on electronic degrees of freedom. We have a general plan to use atomic orbitals that are similar to orbitals in hydrogen atom as a building blocks for wave function of the multi-electron system. And we need a reliable procedure how to use this building block to find the wave function. Why do we need wave function? Does any of us measure wave function? Like there is a spectrometer and there is a wave function meter. No. So no one measures wave function. Why do we care about it?
To get an observable, you take the conjugated product where the operator is acting on the wave function.
I agree. So if we do have wave function and we do have an operator for an observable that we measure in apparatus, we merge them in the prescribed way and get a number. So wave function is an intermediate object, mathematical object, that allows to obtain any observable. So as soon as we have wave function, we easier not to have anything what can be measured. So by now we target finding wave function. Good. The major challenge for electronic problem was and is to treat a system, a wave function with many independent variables, electronic coordinates, and therefore we split it in building blocks and use this single electron wave functions as the building blocks. But how they come into this big wave function? We do not have a exact path how to get to the answer, but approximate direction is to construct Slater determinants and get use of them. And we are spending a little bit more time to get a general idea where a Slater determinant comes from, and how a little bit more understanding how we construct big wave function of the small basis functions. So this meeting is also not super useful. The real important meeting will be next Tuesday. Now it's still a little supplemental information that will help to go forward. So we are going to briefly look through system of two electrons and look for their eigenstate. As an overview, we are not going to derive much things because it will be exhausting 1, time spending 2, and it is not goal of the course 3. But we will get a flavor how these antisymmetric products, where the Slater determinants are coming from. What else?
We can't see anything.
You cannot see anything. It's not good. You should see everything. And another thing that we should get prepared to is to complement our theoretical background with a little self-teaching practical session where we will make presentations and share our accumulated skills with each other in a similar way as we did before for model building. So I will keep talking to you and developing this list, but there should be about 10 subjects. And there will be, maybe on Tuesday or next Thursday, I will print it, distribute in class so that each of you will mark your selection, and then we'll target 3 minutes presentations, but as you have seen in practice, it takes about more than 5 minutes to present and a couple minutes more to answer questions. We went through only few we are about less than 20% done with this list. But as we meet in the labs, we will get more and more skills, and then individuals who select one or other subject can master their skills and share with others, so that we all will feel very comfortable. There was we are slowly moving from graphical user interface to the text-operated running of the computational chemistry jobs. And at the end of the course, if you select to complement your research by computational component, most of the time you will be like looking into a black screen with white letters and typing something. Not because it is most pleasant thing in the world, but because it is much quicker than to click mouse if it gets with many jobs. So here is the very brief glance forward to what we will be doing when we meet next time in the lab. So before we were preparing the input file for Gaussian and submitting the job in the command line, right? There is a way to open this input file in the command line in a text editor and make an educated corrections. Change something manually and submit the job. We already have learned that modifying geometry by hand by typing something is not a good idea, but modifying the method, basis set, the actual assignment, whether we want to optimize or find total energy, is very legitimate and good thing to modify by altering the input file for Gaussian. So we'll be going through this file and learning what does it contain and how to modify it. And another thing that we didn't get to last night is reading of the output file, .log file. We made our first step toward it through discovery by Jared, and you do see it on the first line. So if you look for the text SCF done, then you can get the total energy of the system. But there are some additional helpful information that we will look how to extract and how to get use and how to correlate them with observables. So here is the simplest way to look just on the menus, menu tabs. And this is something that is too early now, but we will get through in the web. And if time will allow, next Wednesday we'll do this electronic clouds images. If not, we will postpone it for 1 week more. Okay, so a context, where we are now and what we are doing and why we want to say a few words more on slated determinant, why this concept is important. Here is a little cartoon. I'm not sure if I can draw it better this time, but it was drawn in a couple of seconds in the same circumstances. So consider that we have blue ions which have positive sides. Am I blocking your way? Or it is not so important that you don't care about what? So blue ions that attract electrons, and then we submit, let's say, first electron to the system. So first we remove everything, have only positively charged ions. Then we throw in one electron, and we know that electron is not a particle, it is a wave, it distributes in space. And this red electron distributes approximately around each ion. Right? Okay, now we nail down this electron too and submit a second electron. And second electron will feel both attraction from ions and repulsion from the first electron. But the first electron will consolidate around ions. So the second electron will decide to go in the spots between ions or a little apart. So because of repulsion between electrons, the second electron will come to spots in the space which were available. And quantitative treatment of this different distribution of electrons comes from electron-electron repulsion, and we need to go into the details, how to take into account energy of electron repulsion with take into account of anti-symmetry principle, Slater determinant. So we look through the next week. We will merge together Slater determinant and Coulomb repulsion, and as a result, we will see that there are some exotic terms. One of them is exchange, Coulomb and exchange, that contribute to the Hamiltonian, that allow to solve this equation and find a wave function. So the actual thing is simple. If one makes it in a review session, one can prepare it as one-page PowerPoint slide. But we are going slowly but surely so that the ideas are not new for us anymore. So we are going to look how this distribution of electrons around ions is happening. And now we are going to look onto the auxiliary system of two electrons. So it is not a practical problem. If we would do some super advanced course in quantum chemistry, we would probably consider helium atom by pen and paper calculation. But do not worry, we are not going to do it today and in this course at all, although it is possible. But if we do have two electrons, both can be up and down. And as we agreed with this all from last time, there is a superposition of up and down for speed 1 and for speed 2. So there is this sigma spin wave function for one spin, and there should be the same sigma wave function for the second spin. How do we deal with wave function for system of two spins? So I'm going to make it a little more entertaining and just quickly draw it on the blackboard. So if you have spin of electron 1, it is a superposition of alpha and beta for electron 1 with coefficients. C alpha 1, C beta 1. And if you do have second electron in state alpha, second electron in state beta, means up and down. Suppose we do not have any explicit interaction, so we can construct big wave function as product of small wave functions. So if we do just open, if you do open brackets, we do see that the system of two spins can exist in either one of four states. First spin in state alpha, second spin in state alpha, first spin in state alpha, second spin in state beta, first spin in state beta, second spin in state alpha, first spin in state beta, second spin in state beta. And in general, if we want to allow interaction with them instead of products of this one electron orbitals, one electron states, we can just add coefficients in front of each basis state. So it means that both spins up, both spins down, and either up and down, down and up. Any comments or objections here? Or you? Oh, okay. This is too abstract. So abstract that it is boring. But what is the connection to practical world? Not any value of this C coefficients is good and correct. The only preferred set of these C values would correspond to real world. So for state of two spins, one state of these two spins, we need set of coefficients. C alpha beta, C beta alpha, C beta beta. And this set of coefficients is unknown. So we need to find these four coefficients, like vector of state for system of two spins. And the values of these coefficients can be found from equation that is similar to Schrödinger equation, but a little different because it is eigenvalue for spin operators. Z. So the operator for total spin acting on this wave function should give the same wave function. And solution of such equation will provide the values of total spin and values of this expansion coefficients. It will be boring, not very long. I promise that in half an hour you will have no boring things for a long time. So it's the same thing is here. So we do have a superposition of several basis states of spin system. The solution of this problem is would take a little longer time than we have here, but it is based on making the total operation of spin by adding together spin of system 1, spin of system 2 as a vector summation, because each spin can be composed as three projections, x, y, and z for first, x, y, and z for second. One add them together as a big operator and find its matrix element and uses this operator to convert it into a matrix form. Since now I'm getting a very big jump forward because I don't want to exhaust you and I don't want to exhaust myself. Here, if you are very curious, here is how this operator of total spin look in respect to spin operators that you were doing in the homework, resonant lowering. And here is the result of acting by this total spin square operator on all of the basis states. So when both are up, both are down, and the cross terms. So when I want to apply this operator to this stuff, the first term will be the same in each case. And the last term will be 0 for up, up, and down, down, and it will get the cross terms for the intermediate. So if we are acting on spin up, spin down state, we get both spin up, spin down, and spin down, spin up. So there is a flip due to this resonant lowering as you did in the homework. And if you apply it to down up, it also, as a result, you get down up and up down. But they are simultaneous. And the simultaneous appearance of these two states as a result of action of this one makes the matrix of this operator. It's not here. Okay, then I can practice showing it on the blackboard. So I'm skipping the constant, which will be like h squared c4, and it will be diagonal elements. Here will be zeros. And there will be two off-diagonal elements. When these off-diagonal elements appear due to spin flips in these total spin operators. So the problem of finding the eigenstates of total spin operator are equivalent to diagonalizing this 4x4 matrix. And this matrix is applied to this vector. So if we recast this equation in a matrix form, then it will be this matrix times this. So it is finding such eigenvalue and such values for this vector that will satisfy this equation. And if one does it, there appear 4 solutions. Thank you. Or if you do it, then one gets 4 solutions with 2 solutions that come from the first element in the matrix and the very last element in the matrix. They give solution when the coefficient is 1, 0, 0, 0, or 3 times 0 and then 1. So just the basis states, all up and all down. They are eigenstates. And due to diagonalization of this little block in the middle, one gets 2 linear combinations. So it is a superposition of up, down, down, up with plus or minus. And the superposition of this up, down, down, up corresponds to projection of total spin 0 and magnetic projection 0, and is corresponding to a singlet state, which is typical for most of the molecules. So it is not a rigorous derivation of this later determinant, but it shows a path how one can rigorously come to such combination of basis functions. So if one deals with many electrons, then one is getting superposition of products in a natural way, just through a standard procedure of eigenstates finding. but Slater determinant definition is educated guess that is found to work all the time. So no one was trying to solve this equation for like 10 or 50 electrons. One just made a limiting case how this combination should look for 2, 3, 4, 5 electrons and such. So in the form of this Slater determinant. So if you do not believe it, you can practice diagonalization of this matrix. So from now on, let's accept that we agree with antisymmetric form of a wave function with the determinant, and when we meet next time, we are going to merge together the fact that a big wave function of all electrons in the system is combined of individual products according to Slater procedure, but in order to construct energy operator, Hamiltonian, of the overall molecule for many electron problems, there will be appearing Coulomb terms with different combinations of the building blocks of elementary atomic functions. So we will just carefully look for any possible contributions from Coulomb term and how they look on what we do have on the left and the right of this, so to say, matrix element. When we were, well, some of us were meeting in quantum chemistry class. And there, the class was super simple in some sense because it was always dealing with one electron only. So when we were talking about matrix elements, we had an operator, wave function of one electron on one side, wave function of one electron on the other side. The challenge for multi-electron problems in general and computational chemistry in specific is that we will be dealing with matrix elements that have two wave functions on the left and two wave functions on the right. We are not going to solve anything ourselves, but we just need to carefully take into account how to treat these matrix elements. What were we talking about?
For diagonalization.
And later we made an observation that if we do practice multi-electronic problems, we will have matrix elements that have several elementary functions on the left and the right of the operator. Okay? I think that's it. Any questions? Any questions about homeworks, about our plans?
Yes, we do.
Or no one minds to have a little early completion?
No, we're good.
Yeah.
They're good? Okay. Okay, then
Minimum energy condition.
what should I do?
Pass again.
How do we do it?
I think it's 2 or 1.
I think 1 is the audience and 2 is the studio. So
Adjourn.
yeah, adjourn. Meeting number 11 is dismissed. Looking forward to see you and your homeworks on next Tuesday.
So I have a question on the homework. On A, are we supposed to do methane or methane?
Yeah. Does it really mean?
Because methane, I don't know if it's stable.
Do not practice n equal 1. Start from n equal 2.
So I need to make 5 models for A, n equals to 2, n equals to 3, n equals to 4, like that.
Mm-hmm.
Methane?
Yeah.
For each of these models, I need to provide these three.
Yes. Yes.
5 into 315.
Huh?
Okay.
I have only one.
And for the second one too.
No, you just send me. And
What is? No, 4. From 1 to 4.
So I need to make 4 models here, right?
Yes. After you get all skills, how to, even if you haven't drawn them, if you do it again and again, it will be very quick. Just 10 seconds to add a couple of items.
I think if you went through how to get that matrix, it would come up that way. However, I don't see how you diagonalize a matrix with zeros everywhere except that. How will you diagonalize that? Because if you take row 2 minus row 1, row 3, you get 0. So then it'd just be 2 and 2 and everything else zeros.
I do not mind to show this.
It's probably something, but my brain
It is.
is not.
Oh, my goal is achieved. You do not download the form of the matrix, which is much harder. The organization is easier.
No, she was doubting why 02 and. But then I said that's how it counts, and I was like,
It takes like hour and a half to do the details. Well, if you do it for the first time. For the matrix, I'll do this. So let's replace this with just by eigenvalue, unknown eigenvalue.
oh yeah, you
And
can.
you do
Okay,
2
yeah.
minus 1 to 0, 0, 0, 1 minus 1 to
Okay,
1.
I got it now.
Again, you make it equal to 0 and find eigenvalues, then plug it in and find eigenvalues.
Linear algebra. We had to take that.
You haven't?
No, we had to take that, but that class.
it's offered in last.
Did you learn a lot in the class?
I had a grad student teach me stuff on
Yeah, I had a grad student, and then like in his office it was another grad student, and it was just like they didn't care. I was just happy I didn't have to take 129.
I'll try this.
Oh, then you actually probably.